We've always looked to the stars as our final destination, the next frontier. It's a core part of the human story. Movies, books, and our own imaginations tell us that with the right engine, or some brilliant discovery, we'll one day become a starfaring species. We see those pinpricks of light in the night sky and picture ourselves planting a flag on a new world. It feels like our destiny. But what if the problem isn't our technology? What if the universe itself has put up a permanent, unbreakable wall around our solar system, with the laws of physics as the bricks? The romantic vision of zipping between stars is one of our most cherished dreams. The reality, though, is a brutal collision with cold, hard numbers. The challenge isn't just about building a better rocket. It's that the universe simply wasn't built for travel. Today, we're not talking about engineering problems we might solve one day. We're talking about the fundamental rules of the cosmos that make reaching even the nearest star a near impossibility. The first barrier isn't a complex equation or a mind-bending theory. It's the simplest, most profound, and most humbling obstacle of all: distance. The scale of the cosmos is so far beyond our experience that words just don't do it justice. But let's try. Our nearest stellar neighbor is Proxima Centauri. It's about 4.24 light-years away. That number sounds small, 4.24. But a light-year is the distance light travels in a year, moving at an incredible 300,000 kilometers per second. It's a measure of distance, not time, and it's immense. About 9.5 trillion kilometers, or 6 trillion miles. So, Proxima Centauri is about 40 trillion kilometers, or 25 trillion miles, away. Numbers that large are basically meaningless. So let's shrink it down. Imagine the sun is the size of a single grain of sand. At this scale, Earth is a microscopic speck orbiting about an inch away. Mars is an inch and a half away, and Jupiter is about 5 inches out. Our entire solar system, out to Pluto, would fit inside a small room. On this same scale, where is Proxima Centauri, our very nearest neighbor? It's not in the next room. It's not down the street, it's 4 miles away. 4 miles of empty space separating one grain of sand from the next. We've sent probes into that void. Voyager 1 is the farthest human-made object from Earth. After traveling for nearly 50 years on our sand grain scale, it hasn't even crossed the length of a football field. It would take Voyager over 70,000 years to reach Proxima Centauri. The fastest crewed spacecraft in history, Apollo 10, reached a blistering 39,897 kilometers per hour, about 24,791 miles per hour, on its return from the moon. But even it would need around 115,000 years to make the trip. Our uncrewed probes are much faster, with the Parker Solar Probe setting a record of roughly 692,000 kilometers per hour, 430,000 miles per hour, in late 2024. Still, even at that incredible speed, the journey would take thousands of years. This isn't about building a slightly faster ship. The distances are so vast, they make our entire idea of travel obsolete. This is the tyranny of distance. So, the obvious answer is to just go faster, right? Why can't we build an engine that goes, say, half the speed of light? Well, that's where we hit our next wall. And this one isn't a suggestion, it's a law. In sci-fi, we have warp drives and hyperspace. These are wonderful plot devices, but they clash with the most fundamental rule of our reality. The universe has a speed limit. That limit is the speed of light. And it's not just a record to be broken. It's a fundamental property of space-time itself. It's the speed of cause and effect. According to Einstein's theory of special relativity, as an object with mass gets closer to the speed of light, it gets heavier. Not just a little, exponentially. As you approach 99.9% of the speed of light, your mass starts ballooning toward infinity. And to push an infinitely massive object, you need an infinite amount of energy. It's not a technological problem. It's a physical impossibility. Nothing with mass can reach the speed of light, let alone break it. Physicists are pretty united on this. While some theories speculate about loopholes like wormholes, shortcuts through space-time, they come with their own universe of problems. Creating a stable wormhole would probably require a hypothetical substance called negative energy that may not even exist. Even if it did, the energy needed might equal that of an entire galaxy. Plus, the wormhole would likely be violently unstable, either collapsing on you or bathing you in lethal radiation. So, faster than light travel is off the table. Einstein's laws are the rule. This means we're stuck on the slow road. But even if we aim for speeds below the speed of light, we run headfirst into our next barrier. The universe demands a payment for speed, and the bill is impossibly high. Let's be generous. Let's say we're not trying to break the light barrier. Let's aim for a modest 10% of the speed of light, or about 30,000 kilometers per second. That would get a probe to Proxima Centauri in about 42 years. A journey at least within a human lifespan. But getting a spacecraft to this speed is where we confront the tyranny of the rocket equation. The rocket equation is a cruel master. To go faster, you need more fuel. But that fuel has mass. To accelerate that extra mass, you need even more fuel. And to accelerate that fuel, you need, well, you see the problem. The numbers quickly spiral into absurdity. To accelerate just 1 ton, the weight of a small car, to 10% of the speed of light would require 450 petajoules of energy. That's a hard number to wrap your head around, but it's about 125 terawatt hours. For perspective, the entire world's primary energy consumption in 2023 was around 170,000 terawatt hours. So, accelerating a small payload to a fraction of light speed would require a significant portion of all the energy used by our entire planet for a year. And that's assuming 100% efficiency, which is impossible. Even our best theoretical propulsion systems can't escape this trap. Chemical rockets, like the ones that took us to the moon, are laughably inefficient for this kind of trip. Fusion engines, harnessing the power of a tiny star, are better. They could theoretically convert about 0.7% of their fuel's mass into energy. But to make a round trip with a meaningful payload, you'd need a fuel tank larger than a planet. The most powerful energy source imaginable is matter-antimatter annihilation, where 100% of the mass is converted to energy. The perfect fuel. But creating antimatter is so difficult that a single gram is estimated to cost over $1 trillion. Then you have to store it. A containment failure for just a few kilograms would cause an explosion that makes the largest nuclear weapons look like firecrackers. So the energy required isn't just expensive, it's civilization-endingly huge. We simply can't afford the ticket. But even if we could, the universe has another nasty surprise waiting for us. The space between stars is often called a vacuum, but it isn't truly empty. It's filled with a thin soup of gas, dust, and micrometeoroids. At the speeds we're used to, this isn't a huge problem. But at relativistic speeds, this thin soup becomes a deadly sandblaster. Think of it like driving in the rain. If you're walking, raindrops fall on you gently. If you're driving at 70 miles per hour, they smack your windshield with force. Now, imagine you're traveling at half the speed of light. A single hydrogen atom, the most common thing in space, hits your ship with the energy of a particle in a high-speed accelerator. The constant bombardment would become a stream of hard radiation. Studies suggest that at speeds approaching half the speed of light, the radiation from interstellar hydrogen would likely become lethal to a human crew, even with significant shielding. It creates a paradox. The speed you need to make the trip in a reasonable time would kill you long before you got there. And that's just the gas. The bigger problem is dust. At 50% of the speed of light, hitting a single pebble would release an explosion comparable to a small bomb. The kinetic energy is just that enormous. You can't just dodge it either. By the time your sensors spot a pebble 1,000 kilometers ahead, you'd have a fraction of a second to react. What kind of shield can withstand a constant barrage of hypervelocity impacts? So, the empty void is actually a minefield. Go too fast, and you're either irradiated to death or obliterated by a grain of sand. This forces a speed limit on us that's far below what we'd want, making the journeys even longer and bringing us right back to the problem of distance. Let's step back from physics and talk about the brutal economics. Even if we could solve all of the above, who would pay for it? A study for a 1970s mission concept called Project Daedalus, an uncrewed probe to a nearby star, gives us a hint. While cost estimates vary wildly, some adjusted for inflation figures for such a massive undertaking have been placed in the tens of trillions of dollars, with some early projections going even higher. For context, the entire world's GDP is around $100 trillion. The Apollo program, humanity's greatest technological achievement, cost about $150 to $288 billion in today's money. An interstellar mission could be orders of magnitude more expensive. What government or group of nations could possibly sustain that kind of funding over the decades it would take to build? This brings us to the final, and perhaps most human, barrier: time. The journeys are long, decades at best, more likely centuries. This introduces the weirdness of time dilation. As you approach the speed of light, time for you slows down relative to time back on Earth. But this effect is often overstated. At the modest 10% of light speed we talked about, a 40-year journey for you would only be a few months shorter than for the people on Earth. The effect is minimal. For the dramatic time slowing seen in movies, you need to be traveling at 99.9% of light speed or more. But if you did that, you'd create a heartbreaking disconnect. If you travel to a star and back, a journey taking maybe 20 years of your life, you could return to an Earth where centuries have passed. Everyone you knew, everything you cared about, gone. You would be an exile, a stranger on your own home world. Communication would be impossible. A simple hello would take over 4 years to reach Earth from Proxima Centauri, and a reply would take another 4. You would be completely, totally alone. So where does that leave us? The tyranny of distance, the unbreakable speed limit, the impossible energy costs, the lethal void, and the crushing timescales all build a case that is not just difficult, but seemingly final. The laws of physics themselves have effectively built a cage around our solar system. It's easy to see this as a depressing thought, the dream of the stars denied. But maybe there's another way to look at it. Perhaps the universe isn't imprisoning us, but is instead telling us something profound. Our inability to leave makes this solar system infinitely more precious. This pale blue dot isn't just a starting line, it's our only home. The fact that we're stuck here doesn't have to be a tragedy. It can be a powerful reason to protect the only habitable world we know and to cherish our shared existence on this fragile rock. And the dream of the stars isn't dead. The real miracle isn't traveling to the stars, but understanding them from where we stand. With telescopes like Hubble and the James Webb Space Telescope, we are already interstellar travelers. We journey billions of light years with our eyes and our minds. We can witness the birth of stars, the death of galaxies, and the faint light of distant planets, all without ever leaving home. The universe may have forbidden us from touching the stars, but it has given us the power to comprehend them. And maybe, just maybe, that is an even greater gift. If you had a one-way ticket to a planet orbiting Proxima Centauri, knowing you could never come back and everyone you know would be gone, would you take it? Let us know in the comments.